Okay, let us continue with the design of a two-stage op-amp circuit. So as we saw in the previous video, for this circuit, two-stage operation circuit with compensation, Miller compensation capacitor, having 7 MOSFETs. So we obtained the transfer function having 2 poles and a 0. The poles are there on the left hand side and there is a 0 on to the right hand side. We actually obtained the location of poles and zeros also. This is exactly the location of poles and zeros. So minus of on the S plane. So this is on S plane we have at minus omega. This is after compensation minus omega P1 and P1 dash was the initial portion. P1 is the after compensation. P2 dash is before compensation and this is after compensation. I can write this as this is before compensation and these two are after compensation. These two are, they're not actually zeros, they're actually poles. These two are after compensation and of course this is a 0 coming upon doing the compensation. So we know, okay, these are all the poles and zeros. So if you write the Bode plot of uncompensated and the compensated one, so this is, I'm writing only the magnitude plot of the Bode plot. So it goes this way. It will want to have a constant gain and it will want to have one pole and there is a second pole. This is omega P1 dash, this is omega P2 dash. So this is omega. This is the graph corresponding to without compensation capacitor. So with compensation the circuit, the plot changes. Of course the gain is still A0. The gain is A0 where A0 is given by GM1 R1 and GM2 R2. With compensation the plot, we know that this pole will go to more here and this pole will go to more far. This is how it goes, and then it will going to have a slope of 20 dB per decade, exactly the same thing. It almost coincides with the previous one and it slightly moves ahead, and then here we're going to have this is omega P1. As we saw, omega P1 dash frequency actually reduces, which is exactly seen here. Can you see this frequency actually reduces? The same thing is seen in the Bode plot. Whereas this frequency will further increase, so it has actually went to a larger frequency. Now this is, there is an increment in the slope here. This is omega P2, and if I further proceed and write the zero will actually come somewhere here. So this is my omega z. You can see the slope further increases. You can see now this is first pole position, which is due to this. If you're just relating, these two are related here, and you have this coming over, this is coming over here. Actually this is over here, and this one is this is 0. You can see first it is minus 20 dB per decade, then it is here it is minus 20 dB per decade, and there is minus 40 dB per decade, and then again it changes to minus 20 dB per decade. So there is a pole, second pole, and a 0 and a 0. The impact of this movement of poles will certainly improve the phase margin of the system. We know that phase margin can be found out if we know what is the gain crossover frequency. So we are supposed to know what is gain crossover frequency, so which is exactly over here. So this is omega GC, let me call it as omega GC. If you can carefully look at this blue plot at frequency corresponding to omega GC, of course we have totally how many terms? One is A0 term, and we have a pole term here. There is a second pole term, there is a third zero term. So we actually have this term corresponding to DC gain, this term actually corresponds to, of course the exact terms or exact values are, this is one term corresponding to E0, this is a second term corresponding to the location of 0, this is the location of omega P1, this is the location of omega P2. But while finding out the gain crossover frequency, we have to consider only those terms which are responsible for this magnitude plot. So at this frequency, for the compensated graph, only we have two terms which are contributing to the magnitude plot at this frequency, because this is actually omega GC. At omega equal to omega GC, the terms contributing out of these are only GM1 R1, GM2 R2, it is the term corresponding to this, and the other term that is corresponding is only this. So why it is only this term? Why not these two terms are not contributing at this frequency? Because at this frequency their contribution of your omega P2 and omega Z are actually 0, because it's in time constant form. They are not actually contributing at this frequency. So we are concentrating only term A0 and this particular term, and the other term is 1 over 1 plus S CC R2 GM2 R. So these are the terms. Suppose now we know that at this frequency magnitude of VFS V0 of S by Vn of S is actually equal to 1, is actually, because it is unity gain. This is actually 0 dB or 1 volt per volt is the gain. So what you can do is you can simply equate this to 1 and you can try to get the expression for omega GC. So now it is GM1 R1 GM2 R2. What is the magnitude of this one? So magnitude of this is under root of 1 plus, of course since it is j omega, so omega is now omega GC. I can write it as omega GC whole square, sorry, omega GC plus CC R2 GM2 and then R1 whole square under root. So you can certainly take out this square root and this, because this is negligible compared to this quantity, so that now you can write 1 is equal to GM1. We are actually trying to get an expression for gain crossover frequency omega GC. So we are equating the magnitude to 1 and we are considering the terms that are corresponding at this frequency. The terms contributing are the magnitude term and omega P1 term. This GM1 R1 GM2 R2, because taking out this square root and square, so I will end up with omega GC CC R2 GM2 and then R1. So we can take out the terms which are, I can take out this, I can take out this, so I'm left out with is equal to GM1 by omega GC into CC. Therefore, omega GC, the gain crossover frequency is given by to the value, it is GM CC. This is gain crossover frequency of a compensated two-stage op-amp is given by GM1 by CC, GM1 by CC. So here what we are assuming that GM2 is too far away from the gain crossover frequency, and of course omega z, that is the 0 of the transfer function is also too far away from the gain loss of frequency. So with this in our mind, so let us try to find out what is the phase margin of this system. So let us try to find out what is the phase margin. So the phase contributed by all the terms are, of course, this is, of course, let us write this particular term. So what is this term? It is actually minus of tan inverse of, it is omega by omega p1 minus tan inverse of omega by omega p2 and plus tan inverse of minus omega by omega z. Okay, these are the terms that are contributed by two poles and a zero and a zero. Why this is negative means because I have this as negative term. This is because of this minus. I have this as minus, and of course these two are minus because it's a pole. It is plus because it is a pole, the phase contributed by zero. So let us, of course, for finding out phase margin, omega should be equal to omega gc. So let us substitute wherever omega is there by omega gc. This is minus tan inverse of omega gc by omega p1 minus of tan inverse of omega gc by omega p2. This small modification we'll do here. Instead of writing tan inverse of minus omega by omega z, let me write it as plus of 180 minus tan inverse of omega by omega z. So this is the small correction what we are doing because of this negative sign. So now let us try to substitute the values of omega gc and omega p1, and what is of course we assume that omega, of course this is omega gc let it be, sorry, omega z let it be at least 10 times that of omega gc. So we are assuming that 0, it is whatever 0 you have here, is too far away from the gain process frequency. Let us assume that it is at least 10 times away, so that it doesn't affect our, it doesn't deteriorate the phase margin. In order to have a larger phase margin, I need to have 0 to be far away from the gain crossover frequency. For that we are assuming that, so this is assume this. So when you are assuming this, let us see what happens. So it is minus tan inverse of what is omega gc. Omega gc, if you know, omega gc is given by the expression, okay, omega gc is gm1 by cc. It is gm1 by cc, and what is 1 over omega, so what we have is, this is 1 over omega p1. So we know that omega p1, so if I write omega p1 is what, it's actually 1 over r1 cc gm2 r2. So let us write that. So since it is 1 over, I can write it as, it is r1 cc gm2 r2. So this is the expression. Of course this is actually gm1 by cc, gm1 by cc. If you can see here, this is gm1, omega gc is gm1 by cc, so that I can write it is gm1 by cc multiplied by this. So this will go with this, so you end up with the first term. Let me just complete the first term. It is minus tan inverse of gm1 r1 gm2 r2 minus, let me write it as tan inverse of omega gc by omega P2. Since we know that this is omega z is 10 times that of omega gc, so let me write it as minus tan inverse of omega gc by 10 times of omega gc. So this becomes 0.1. If you can see here, this is actually a naught. Is it not a naught here? Since it is a naught, it's a very large quantity. Tan inverse of a very large value is actually minus 90 degree. Because tan inverse of a very large value is 90 degree. So since it is minus that, it is minus 90 degree. Let us write it as what is tan inverse of omega gc by omega p2. So what is, this is actually tan inverse of 0.1. So what is tan inverse of 0.1? Tan inverse of 0.1 is actually 5.7 degrees. Oh, okay, we just missed out this 180 degree. So let us write it as plus 180 minus, okay, now it is plus 180 degree minus 5.71 degree. So this is actually PM. So in this particular expression, what we are trying to find out is, we are trying to locate what should be omega p2 for a given phase margin. So let us assume that let phase margin be around 60 degrees. If you want to have a phase margin of around 60 degree, where do you want to locate the second pole? Where do you want to locate the second pole? The second pole location can be known if you know what is the required phase margin. So required phase margin is 60 degrees. So let me write it as 60 is equal to minus 90 minus tan inverse of omega gc by omega p2. It is plus 180 degree minus 5.7. So this, if you can simplify this, then it becomes tan inverse of omega gc by omega 2 is equal to, it is minus 90 minus 60 minus 5.71 plus 180. It is now, let me write 90 plus 60 plus 5.71 minus 180. So it is 24.29 degrees. So that omega gc by omega p2 happens to be tan of 24.29, which is, okay, let me write tan of 24.29 is 0.451. So what does it mean is, omega p2 should be omega gc by 0.451, and that is 2.21 times omega gc, meaning this is omega p2 is equal to 2.2 times omega gc. That means to say, if you want to have a phase margin of 60 degree for a given second order system, or for the two-stage opamp, I should locate the second pole in such a way that second pole should be located at 2.2 times omega gc. 2.2 times omega gc. Assume that instead of 60 degree, if you want to have a 75 degree phase margin, then this becomes 75 degree. So then let me just find out what will be the location of your omega p2. So it is now, of course it will be 24.29 minus of 15 degree, it is 9 point something. Tan of answer is this actually. So then it would be, you can see then omega p2 should be located at 6.11 times omega gc if you want to have a phase margin of 75 degree. If you want to have a phase margin of 60 degree, then omega p2 should be located at 2.2 times omega gc. So this is exactly what I mean to say here is, this is omega gc. What should be this if you want to have a 60 degree phase margin? So this should be at least 2.2 times omega gc. If you want to have 75 degree phase margin, then this should be at 6.1 times from this particular omega GC frequency. So that's what is the meaning of location of second pole. Location of first pole will not too much affect, of course. The phase margin is decided by the location of second pole, and of course we are assuming that the 0 is located at 10 times omega GC, 10 times omega GC. So this is with this assumption. So the second pole should be at 2.2 times omega GC for 60% or 60-degree phase margin. If you want to have 75-degree phase margin, then it should be at 6.11 times omega GC. So in the next videos, we will exactly do the design of a two-stage operational amplifier with given specifications, and then try to identify the dimensions of all these transistors, and then try to simulate few problems.